So in this video, I want to talk a little bit about the comparison test and do a basic example. Now, the comparison test can be used for convergence or divergence, and it says that if we see that the sequence a sub n is always going to be less than or equal to b sub n for all n, with all positive terms, non-zero terms, then if b sub n converges, because b sub n is bigger, then the series of b sub n must be larger than the series of a sub n, so the series of a sub n must converge. If a sub n diverges, so now a sub n is the smaller one, then b sub n must diverge. This works exactly like the comparison test for improper integrals. Basically, if we have a convergent series, anything smaller than any series we can show is smaller must converge, because it's smaller than something convergent. If we have a divergent series, then anything larger than that, any series we can show larger, must diverge, because it's bigger than something that we already know diverges. So I'm going to do a basic example and just we'll walk through the steps a little bit. So we're looking at the series from n equals 1 to infinity of 1 over n squared plus 1. So we notice that this is really close to 1 over n squared, which we know is convergent. That can be shown a couple different ways. One way is with the integral test. 1 over n squared plus 1. Actually, it's not a bad integral, but I want to practice using the ratio test. So this is similar to 1 over n squared. So I've already got the idea in my head that it is going to converge. So 1 over n squared would be what I'd want to compare it to. So I want to show, and I like to use WTS for want to show, that 1 over n squared plus 1 is less than or equal to 1 over n squared. Because I know that the series of 1 over n squared is convergent. So this is what we want to show, and if you get a hunch or if you feel pretty strongly that this is a true statement, what I recommend is working backwards to bring it down to a case where it's obvious. Well, one thing we can do is we can flip both of these. So I have n squared plus 1 versus n squared. Now if I flip both sides of my proportion, that flips the inequality. And now we're only concerned for n, and n is an integer is greater than or equal to 1. This is clearly a true statement, that n squared plus 1 is greater than or equal to n squared. Since n is greater than or equal to 1, the other thing we can put in here, we need to say that the terms were non-negative. That's going to be clearly true. So we have the inequality that we want. We show this is less than something that's convergent. And we can actually, from here, draw our conclusion that the series 1 over n squared plus 1 is convergent by comparison test. Right? Now again, in this video and a couple of the other videos, I'm just going to do some basic examples because I want to talk about the test. If you want to see some more difficult examples, if you have some series that you're wondering about, you can always email them to me and we'll see what we can do. But that's a little basic example of the comparison test.